Hello once again to all my students, viewers, and subscribers, and welcome back to my lecture series in physics. In this video, I will discuss the concept of electric potential. We will revisit a familiar topic in mechanics and relate it to our present topic. It is also in this topic in which we will relate the potential difference to a familiar quantity in circuit analysis commonly known as voltage. After the discussion of concepts, I will solve several example problems involving electric potential calculation. So, if you're ready, let's start making physics more fun and interesting. In this slide, you can see an image of a lightning. We know that lightning is a natural electrical phenomenon. It's basically a discharge of static electric charges. Natural phenomena in the atmosphere, which usually takes place during bad weather conditions, cause accumulation of negative electric charges at the bottom of clouds while the upper portion of the cloud becomes positively charged. This accumulation of charges gives rise to extremely high potential difference, which leads to a discharge which we know as lightning. Okay, so this is a lightning strike. We see that a lightning strikes from the cloud towards the ground. Lightning usually takes place inside the clouds, or they may also take place between clouds. But as we see here in this image, it may also take place between a thundercloud, just like this, and the ground. And how does lightning relate to our topic? Because it involves potential difference. Lightning strikes like this one involves several millions of volts of electricity. But before we discuss the main topic, let's have a brief review of a familiar concept in mechanics, which we will also relate to electric potential. Let's revisit the concept of the work. If a force acts on an object and causes that object to move, then work is done, right? So the work done by a force acting on a particle, displacing it from point A to B, is given by this integral. Work is the integral of f dot dl. So here, we see an integral that involves a dot product. Such integral, like this one, is known as a line integral or a path integral. Therefore, work is the line integral of the force. And since work is a line integral because it involves a dot product, work is a scalar quantity. Now, if the force doing the work is conservative, the work can be expressed in terms of the potential energy, which is denoted as U. Okay? So here, what we're trying to say is that if this force, this F, is conservative, we can always express the work done by that force in terms of the potential energy. So, what is the relationship between the work and the potential energy if this force is conservative? The work done is simply equal to the negative of the change in the potential energy. If you may recall, in thermodynamics, we use delta U for the change in internal energy. But this time, delta U represents the change in potential energy. And since it's a change, we can express it as a difference, no? Final minus initial. If the initial is A and the final is B, then the work done is equal to U B minus U A. Okay? The negative of the change in the potential energy. U sub B is the final potential energy and UA is the initial potential energy. So we can rewrite this simply as UA minus UB. Okay, so this is the relationship between the work done and the potential energy if the force which does the work is conservative. Okay, to illustrate this, let us have a ball which is initially elevated from the ground. Initially, the ball is at position A. In this position, it has a certain amount of potential energy. Specifically, it has a gravitational potential energy. If the ball is lowered to its final position B, its potential energy will change. And that change in potential energy, delta U, can be related to the work done in bringing this ball from its initial to its final position. Okay? And we know that the potential energy is equal to mgh. Okay? So, the initial potential energy is mg times the height at point A. And then the final value of the potential energy is mg times the height at point B. Okay? So, if we subtract the two heights, h at A and h at B, we simply get h. Kaya, ang nakuha natin dito is mgh. Okay? So, again, the work done is equal to the negative of the change in the potential energy. In this case, because this is mechanics, the field involved is the gravitational field. However, in our topic today, which is about electric potential, the gravitational field will be replaced by the electric field. If you recall, in our previous discussions, we made an analogy that in mechanics, the mass is analogous to the charge and the gravitational field is analogous to electric field. Kapag kinumpute natin yung force is equal to m times a. This a is the acceleration due to gravity, right? Pwede nating isulat yan as g. So, yun. And in electrostatics, the force is equal to Q multiplied by E. Ayan. So, this mass is analogous to the charge and the gravitational field is analogous to the electric field. Okay? Now, let us relate the work done to the electric field. Ano kaya ang expression ng work kung ang field na involved ay electric field? Imagine we have a test charge which is placed in a uniform electric field. For example, this is the electric field, no? We see that the electric field lines are parallel and are uniformly spaced. So this means we have a uniform electric field E. Now, here is a test charge. This test charge, whose magnitude is Q, will experience a force due to this electric field. This force is denoted by this vector F. So, if this charge is free to move, then it will move, no? And will acquire a certain amount of displacement. This is the displacement, no? We denote it as T. Now, what is the work done? We know that the work is equal to the dot product of the force and the displacement. Okay, so since the electric field is uniform, we can express this force as a product of Q and the electric field. Okay, now we have the work done, which is equal to QE dot D. Okay, so the work done in moving the test charge from its initial position A to its final position B, denoted as WAB, is equal to QE dot D. So again, this is a dot product. To evaluate the dot product, we can calculate this angle theta. If you know the angle theta, then we can write this dot product as QED multiplied by the cosine of theta. And if this force is conservative, we know that the work is equal to the negative of the change in the potential energy. Therefore, the change in potential energy delta U is equal to the negative of this expression, negative of QE dot D. Again, if we know this angle theta, then we can write delta U as negative of QE D multiplied by the cosine of theta. This is quite simple to execute, no? You just have to multiply the given test charge to the magnitude of the given electric field, which is uniform, no, which means it's constant, and multiply it to the cosine of this angle theta. This theta is the angle between the force and the displacement. How about if the electric field is not uniform? Okay, for a non-uniform electric field, for example, we represent the non-uniform electric field using these curved vector fields. Now, if we place a test charge Q at this point, this test charge will experience a force due to the electric field and which will cause it to move. For example, it moves from A to this point B through this path from A to B. So once again, this test charge moves along this path from A to its final position B. Because this charge has been displaced, definitely there is a certain amount of work done. How do we calculate that work? Earlier, the work is just a product because the electric field is uniform. But we can simply multiply Q, E, and D and multiply it by cosine theta because in this case, the electric field is not uniform. To calculate the work done, it is necessary to integrate. But before we integrate, let us get a tiny amount of displacement and represent it as dl. Okay, so this is the incremental displacement. We can calculate the incremental amount of work done, no? dw. That's equal to f dot dl. And we know that this f is equal to q multiplied by e, right? So we're writing dw is equal to qe dot dl. So now to get the total amount of work done from A to B, we just integrate both sides. So again, the total amount of work done from A to B is the integral of this expression. Since this charge has a constant magnitude, we can take it out of the integral sign. Okay? So yung Q nasa labas na lang at ang matitira na lang sa loob is E dot dl. Okay? So the expression for the work done is equal to Q times the integral of E dot dl with a limit from A to B. Okay, so A is the initial position and B is the final position. And again, if we assume that this force is conservative, then this work can be expressed as a difference in potential energies, UA minus UB. Okay, so tandaan po natin ha, the expression for finding the work done in moving a charge in a uniform electric field is given by this Q times the integral of E dot dl from the initial to the final position. This requires evaluation of a dot product. After you evaluate the dot product, you evaluate a definite integral. Okay? Now, let us analyze this expression. If this work is positive, then this means that UA is greater than UB, right? And if B is the final position, then there is a decrease in potential energy because the potential energy at A is greater than the potential energy at B because WAB is positive. Okay? Now, if this work is negative, then the potential at B is greater than the potential at A. And because of that, we can say that there is an increase in the potential energy. And as a general rule, if the field does a positive work on the charge, okay, so if this work is positive, then U decreases. And the charge moves in the same direction as the field. So in this case, kita natin yung direction nung displacement, no, pakanan, is the same as the direction of the field, which is also pakanan. In that case, lumiliit yung potential energy. But if the field does negative work on the charge, this work will be negative and the charge moves in a direction which is opposite the direction of the field. So let us repeat, if the charge moves in the same direction as the field, then the work is positive and the potential energy decreases. But if the charge moves in a direction opposite the field, the work done will be negative and there will be an increase in potential energy. Now I have a question. What if this charge has been displaced from A to B and it traveled directly along this straight line? For example, no? Yun kayang makukuha nating work is parehas lang or magkaiba. Okay, think about it. If this charge moves directly from A to B along this straight line instead of moving along this curved path, will the work be the same or will it be different? Okay, try to think about it. Now, to answer that question, we need to go back to this force. Remember that when this force is conservative, the work can be expressed in terms of the potential energy. And in addition to that, This work is also independent of the path in which the charged particle traveled. So, that means that whether this charge traveled from A to B along this curved path or it travels directly from A to B along this straight line, the work will be the same. Why? Because the force which does the work is a conservative force. So kung i-relate natin to dun sa topic natin sa thermodynamics, di ba? In thermodynamics, the work done is path dependent. Yung path na pinag-uusapan doon is path in the PV diagram. In this case, the path that we're talking about is the actual path traveled by the charged particle. So magkaiba po iyon, ano? So if we're talking about static electric fields, the work done is always independent of the path, and therefore, it depends only on the initial and the final position. Kaya nga sinasabi natin dito, ayan no, the work done is just the difference between UA and UB. No? Kung siya ay independent doon sa path, then saan lang siya nakadepende? Nakadepende lang siya sa initial at saka sa final positions. Okay? Now, let us have a review on some of the important points about the work done involving electrostatic fields. For every electric field due to a static charge distribution. So, once again, let us give emphasis to this. No? The electric field involved is due to static charge distribution. That's why we describe the field as an electrostatic field. We must remember that the force associated with static electric fields is always conservative. And if this force is conservative, then the work done is always equal to the negative of the change in the potential energy. We have also learned that the work done depends only on the initial and the final positions of the charge and is therefore independent of the path traveled. Let us recall the work done in moving a charge in an electrostatic field. That work, remember, is equal to Q times the integral of E dot EL. We integrate it from A to B. Now, to illustrate this, for example, ito yung electric field. Okay? Yan. Itong electric field. Tapos, meron tayo ditong point A kung saan mayroong charge. At yung charge na yan, gagalaw papuntang point B, for example. So, we move the charge from A to B, right? And there is a certain amount of work done. And that work is due to this electric field. Okay, so here we have a charge field system. This work is due to the force that this electric field exerts on this charge. Okay? However, mathematically, we can rewrite this work. If we interchange the limits, this becomes B and this becomes A, then the work done will be equal to the negative of this. Di ba kapag ini-interchange natin yung limits, nagne-negative yung definite integral, so this becomes equal to negative Q times the integral of E dot dl, this time from B to A. Okay? So basically, these two are just the same. No? However, they are written in two different ways. One is from A to B, and this one is from B to A. So, in the first case, the work done is due to the force that this electric field exerts on this charge. And this charge is moved from A to B. Okay? However, if we write this work in terms of this second expression, in which the lower limit is from B and the upper limit is A, then it only means that the charge has been moved from B to A. Okay? So, for example, this is point B, no? And this is point A. Initially, the charge is at point B. So, to move the charge from point B to point A, halimbawa, ito yung point A, then we need to apply a force which will oppose this electric field. Okay? And that force is equal to the negative of the force due to this. So that's just negative of QE, right? Okay. So in the first case, the force due to this electric field is Q multiplied by E. But to move the electric field from B to A, we need to apply an external force, no? Lagyan natin dito ng subscript na EXT, no? to indicate that it's an external force which will oppose this electric field. Kaya dito mayroong negative sign. Okay? So that is how we interpret this second expression. In this case, the work is done by an external force which moves the charge from B to A. Okay, against this electric field. Once again, this expression can be interpreted as the work done by an external force in moving the test charge from B to A against this electric field. Okay, that's why it moves in the opposite direction. No, the negative sign here indicates that this charge Q has been moved from B to A against this electric field. Okay? So usually, ito yung ginagamit for applications. No? Sa electromagnetics, ito yung ginagamit na expression ng work. Okay? May negative, tapos from B to A yung expression. Pero parehas lang tayo ng makukuhang numerical value. No? Yang dalawang yan ay parehas lang equal sa WAB. Magkaiba lang yung ating interpretation. Okay? Now, ano kaya ang mangyayari kapag itong work na ito, yung WAB, ay i-divide natin nung test charge na Q? Diba? Ito yung charge nito Q. Ito yung charge nito Q. Anong mangyayari kapag yung work na ito, dinivide natin ng Q? Sir, bakit mo naman naitanong yan? Kasi, dati, nung dinefine natin yung electric field, it's equal to the force per unit charge. Diba? Okay, so remember that electric field is defined as the force per unit charge. Now, what if yung work na na-compute natin ngayon, i-divide din natin ang charge? May makukuha ba tayong panibagong quantity? Actually, yes. No? That quantity is what we call the potential difference, no? Which is more formally known as the electric potential difference. So how do we define the electric potential difference? Electric potential difference is defined as the work done per unit charge. So if we have a potential difference between 2 points A and B, then we denote the potential difference as VAB. Okay? And that VAB is the work done per unit charge. So once again, this is the definition of the potential difference. Because potential difference is work divided by the charge, and these two are both scalar quantities. The potential difference is also a scalar quantity. And what would be its unit? The unit of potential difference would be the unit of work, which is joule, divided by the unit of charge, which is coulomb. So, 1 joule of work done per coulomb of charge is equivalent to 1 volt of potential difference. So, volt is the unit of potential difference. Sir, di ba yung volt ay unit ng voltage? Yes, actually, yung tinatawag nila na voltage sa electric circuit analysis, yun, yung electric potential difference. Why? Because the voltage between 2 points in a circuit is actually the potential difference between those 2 points. Yung pala yun, ano? Remember that the potential difference and voltage are the same, no? Parehas lang sila ng ibig sabihin. Kaso nga lang, sa circuit analysis, we don't usually call it potential difference because the common terminology is voltage. Why? Because of the unit, no? The unit is called volts. And if between 2 points, there is a difference in potential, that difference is what we call voltage. Okay? Now, if we're talking about an electrostatic field, then we can always express the work in terms of the change in potential energy, right? So this work can be replaced by the negative of the change in potential energy. That's why the potential difference may also be defined in terms of the change in potential energy. Okay? So this delta U is equal to UB minus UA. Okay? Negative of UB minus UA. I just copy the charge in the denominator. If I want to simplify this expression, this becomes UA minus UB. So here, we have UA divided by Q minus UB divided by Q. This UA is the electric potential energy at point A divided by the charge. And this B is the electric potential energy at point B divided by the charge. So in general, the potential energy at a point divided by the charge is equal to the electric potential at that point. So this UA divided by Q is equal to VA, which is the electric potential at A. And this UB divided by Q is the electric potential at point B, written as V sub B. Okay? So the difference in electric potentials between these 2 points A and B is the potential difference VAB. So we now know that the potential difference VAB is equal to VA minus VB. Sulat natin ha, yung VAB is equal to VA minus VB. Therefore, if we have the potential difference Vxy, for example, this Vxy can be written as Vx minus Vy. Is that so? Yes. So tingnan po natin yung order ha. Yung unang subscript, yun yung mauuna. Pangalawang subscript, yun yung pangalawa. Okay? So how do we interpret VAB? Remember that VAB is the potential difference between points A and B. On the other hand, this VA and VB are the electric potentials at points A and B respectively. So if that's a potential difference, you measure it between 2 points. But if that is measured at a point, then that is the electric potential at that point. However, we may also interpret VAB as the potential at A with respect to B. So in that case, the second subscript is our reference. Okay? So for example, Vxy, that can be interpreted as the potential at point X with respect to or relative to the potential at point Y. So again, the second subscript always acts as our reference. Tandaan. Now, kung i-relate naman natin yan sa battery, di ba alam natin na yung battery ay may voltage. For example, meron kang battery na 1.5 volts. That 1.5 volts is the difference in the potentials between the terminals of a battery. We know that a battery has a positive terminal and a negative terminal. So if the voltage is 1.5 volts, then that means that the potential difference between the positive and the negative terminals of that battery is equal to 1.5 volts. Okay? Again, potential difference is the same as voltage. Mas kilala lang talaga siya sa tawag na voltage kasi yun yung ginagamit sa electric circuit applications. Now that we already know the definition of potential difference, otherwise known as voltage, which is the work done per unit charge, express naman natin yung potential difference na ito in terms of the electric field. From its definition, we can express the potential difference in terms of the electric field. Remember that VAB is the work done per unit charge. And this work can be expressed as a line integral, di ba? Yan ay Q times the line integral of E dot dl from A to B. Okay? Lagay natin dito A to B. So, if we divide this by the charge, makakancel yung Q. Diba? At ano na lang ang matitira? Ang matitira yung expression natin ng potential difference, which is the line integral of E dot dl. So, tandaang mabuti, yung potential difference pala, it is just the line integral of the electric field. Kung ang work ay line integral ng force, ang potential difference naman ay line integral ng electric field. What will happen if I will interchange the limits? Diba? Kagaya nung ginawa natin sa work kanina, kapag in-interchange natin yung limits, yung makukuha natin magne-negative lang. Okay, but the numerical value is just the same, no? VAB can also be written as the negative of the line integral of E dot dl from B to A. So, they have the same numerical values, but we can interpret them in two different ways. In the first case, the charge has been moved from A to B by a force due to this electric field. In the second case, this potential difference is the work done per unit charge by an external force which moves the charge from B to A against this electric field. Okay? So again, kapag may negative sign dito, yung force na nag-create ng work para magkaroon ng voltage is an external force na magpapagalaw sa charge mula B naman papunta sa A. So from now on, ito na yung gagamitin nating expression ng potential difference ha. And again, how do we interpret this? This is the work done per unit charge by an external force in moving a test charge from B to A against this electric field E. So yan, meron na tayo ngayong expression ng potential difference in terms of the electric field. Ito ba yung definition ng electric potential difference? No, this is the definition. From this definition, we're able to come up with this formula for the potential difference in terms of the electric field. Okay? In some practical situations, it may also be useful to measure the electric potential at a point rather than the potential difference between 2 points. So, if I want to measure the electric potential, for example, at point A, the electric potential is just VA, no? And at point B, the electric potential is VB. And at any arbitrary point, the electric potential is simply denoted as V. Paano natin malalaman yung expression for the electric potential at a point? So to measure the electric potential at any given point, we may also consider the potential difference, no? Yung VAB, which is equal to VA minus VB. So if we want to measure the potential at point A, then this VAB must be equal to VA, no? And to do that, we need to set VB equal to 0. Okay? So to measure the electric potential at A, we need to set a reference point, which is point B, such that at point B, the electric potential is 0. Okay? So again, para yung VAB ay maging equal na lang sa VA, which is the potential at point A, dapat ang VB na ito ay mag-0. Ano? Pag nag-0 na siya, yung VAB equal na lang sa VA, na ang nire-represent is yung electric potential at point A. So, paano natin yung gagawin? Diba, meron tayong expression na line integral kanina. Remember that VAB is the line integral of E dot dl from B to A. May negative sign dito. What should we do with this expression so that this VAB would be equal to VA? Remember that at point B, the potential is 0. Now, if that is so, then can we replace this B with 0? Kasi at point B, ang potential pala ay 0. So, ang mangyayari niyan, mag-integrate na tayo from 0 to A. Tama ba yan? Actually, mali iyon. Bakit? Because yung 0 na yon ay value ng potential at point B. However, in this expression, the variable is not the potential but rather position. Ayan o, DL. This DL indicates that the variable is position. So, dapat ang ilalagay natin na values ng lower at ng upper limit ay values ng position. No? So, kung ilalagay mo dyan na ang lower limit ay 0, ang ibig sabihin nun, yung charge initially ay nasa origin. Bakit? Kasi sa origin, ang position, 0. Kasi origin yun eh. Diba? 0 ang coordinates nun. Pero sigurado ba tayo na sa origin ay 0 ang potential? We're not sure. Diba? So ano kailangan natin gawin dito? Kailangan ma-realize natin yung position or yung point kung saan yung electric potential ay 0. So isipin natin, where is the electric potential 0? Okay, so far, we know that the electric field is a function of position, di ba? Kung function siya ng position habang lumalayo yung point mula sa source charge, yung electric field ay lumiliit, di ba? Paliit ng paliit yung electric field habang papalayo siya ng papalayo. So, ganun din ba yung trend para sa electric potential? Actually, yes, no? Habang lumalayo yung point doon sa source charge, yung electric potential ay lumiliit ng lumiliit approaching 0. So therefore, the reference point, no, kung saan ang electric potential ay 0, pwede nating iset yan na nasa infinity siya. Okay? Because that is the most convenient reference point, no? Mathematically speaking, okay? To get the value of VA, which is equal to VAB, when point B is at 0 potential, yung lower limit na B gagawin lang nating infinity. Bakit? Kasi nga po, sa infinity, 0 ang electric potential. Okay? Tapos itong R, yan yung distance ng point A mula dun sa source ng electric field. So now we already have the expression for finding the electric potential at any given point. Ano? Paano natin ngayon i-interpret yung electric potential at a point? The electric potential at a point can be thought of as the work done. Diba? Remember, the potential difference is the work done per unit charge. Okay. Dito, ganun pa rin. No? Work done per unit charge pa rin. Pero yung test charge ay na-move mula sa isang point kung saan zero yung electric potential. No? To a given point kung saan natin hinahanap yung electric potential. Again, work done per unit charge pa rin ito. Ang pinagkaiba lang, yung pinanggalingan ng test charge is a point kung saan zero ang electric potential. And conveniently, we set that point to infinity, no? Mathematically speaking. Pero sa totoong buhay, wala namang infinity talaga. Alam namang infinity yung layo, no? In practical situation, sa circuit analysis, meron tayong isang reference point kung saan ang electric potential ay zero. Diba? At familiar na tayo doon, no? Sa isang electric circuit, anong tawag mo doon sa point kung saan ang electric potential ay zero? Diba yun yung ground? Yes! So dito, mai-relate natin yung pinag-aaralan natin sa circuits. Kasi sa circuit, alangan namang ilagay mo yung probe ng voltmeter at a point na infinity ang layo mula dun sa kinukuhanan mo ng voltage, di ba? At saka sa math naman, hindi natin alam kung nasaan yung ground. Kaya hindi natin pwedeng ilagay dito na from ground to R, no? So, conveniently, we use infinity. Kasi sa infinity, pwede nating sabihin na ang electric potential ay zero. But again, in an electric circuit, that reference point in which the potential is zero is usually the ground. Ngayon, mag-derive naman tayo ng expression ng potential difference kung ang source charge ay isang point charge. Okay? So here, let's determine the electric potential difference, VAB, between 2 points due to a point charge located at the origin. So for example, ito yung point charge natin. Ano? Gawin nating positive. No? By default, laging positive yung test charge. Tapos meron tayong 2 points. For example, ito yung A. Tapos ito naman yung B. 'Di ba? So ito yung point A, ito yung point B. Ano nga ulit yung expression for VAB? VAB is equal to negative of the integral of E dot dl from B to A. Ayan. So that means yung test charge ay initially nandito sa B. Dadalhin natin dun sa point A. Ano yung work divided by the charge? Yun yung work done per unit charge na VAB na ating hinahanap. So to solve for that, kinakailangan alam natin yung expression ng electric field na nanggagaling naman dito sa point charge. Ano nga ba yung expression ng electric field na nanggagaling sa isang point charge? Di ba pinag-aralan natin that's equal to K Q over R squared? Yes. So lagay lang natin dito from B to A. Tapos lagyan lang natin dito ng unit vector na AR. Di ba kasi ang electric field by nature is a vector quantity. Saka natin siya i-dot dun sa DL. So ito vector din. Ano ba yung DL? Di yan yung differential displacement because here the variable is R, no? At this point from here to there, yung distance natin is RA. Lagyan natin dito ng label, no? Ito yung RA. Tapos mula naman dito sa source charge hanggang sa point B, yun yung R sub B. Okay? Lagay natin dito, yan yung RB. Yan. So, the variable is R, kaya dito ilalagay natin is dr. Tapos, lagyan din natin ang unit vector na AR. Ano? So, AR.AR is equal to 1. Kaya, pag ito ay ating sinimplify, this will be the negative of the integral from B to A of K Q over R squared dr. Ayan, pwede na tayo ngayong mag-integrate. 'Di ba? Itong K at saka itong Q, constant 'yan, no? Itong Q yung charge na to, no? So dito small letter Q, dito capital letter Q yung inilagay ko. Ano? So sulat lang natin ha, VAB is equal to negative of KQ. Tapos ito i-integrate natin, dr over R squared. Di ba pag in-integrate natin yan, magiging R to the negative 2 dr, na pag in-integrate natin, magiging equal sa 1 over R na may negative 1 dito. na multiplier. Okay? Tapos pag in-evaluate natin yung definite integral, of course, meron tayong lower limit from b to a. Okay? So kapag atin yung in-evaluate, ito negative times negative magpa-positive, 'di ba? Dito may matitira ka na lang na kq multiplied by upper limit. So 1 over r, that is r at point A, minus 1 over r, this time the lower limit, r at point B, which is rb. So we now have the expression for VAB, no? That VAB is equal to KQ times the quantity 1 over RA minus 1 over RB. And remember, this VAB is the potential difference which is equal to VA minus VB. So kung inyong mapapansin, dito sa na-derive nating formula, pwede na tayong mag-deduce na ito palang VA equal pala yan dun sa K Q over R at point A. 'Di ba? At yun namang VB ay equal dun sa KQ over R at point B. Yes. Bakit? Ayun, no? 'Di ba pinag-minus lang natin to. So yung KQ over RA, yun yung VA. Tapos yung KQ over RB, yun yung VB. Yes. So, therefore, nakapag-derive na tayo ngayon ng formula para makompute yung electric potential at any given point. The electric potential at a point is equal to KQ divided by R. Kung saan yung R, yung distance ng point na yon mula doon sa point charge. Pero kanina kung matatandaan ninyo, yung VA na yan ay pwede nating makuha dun sa line integral na ang limit ay infinity. 'Di ba? So, yun yung gagawin natin sa susunod na example, no? Obtain the expression for finding the electric potential at any point having a distance r from a point charge q. Okay? Actually, yun na yung na-compute natin kanina. Ito na yun yung kq over r. Okay? Pero, dito, i-derive natin yung formula na yan gamit yung expression na line integral na ang lower limit ay infinity. Okay? So remember, the electric potential at a point is equal to the negative of the integral of E dot dl from infinity to that point R. Again, this R is the distance from the source charge to the point kung saan hinahanap natin yung electric potential. Okay? So lagay natin dito, ano ba ang pinanggagalingan ng electric field? Isa daw point charge na Q. And the expression for the electric field due to a point charge is KQ over R squared, no? Hindi ko na ilalagay yung AR, no? Ang gagawin ko na lang dito, AR.AR is equal to 1. Rerekta ko na lang siya ng DL at yung DL ay equal dun sa DR. Kagaya nung ginawa natin kanina, no? Lagay natin dito from infinity to R. Okay. So kapag in-evaluate natin ang integral na ito, yung KQ constant yan, may matitira dito na negative 1 over R, di ba? At i-evaluate natin yan from infinity to R. Okay? Negative of negative will give us positive. So therefore, meron dito makukuhang KQ times, okay, upper limit 1 over R minus, okay, what is 1 over infinity? Yung 1 over infinity magsi-0. So, minus 0 na siya. Ayan. So, ngayon, meron na tayong na-derive na formula sa pagkukompute ng electric potential at a point, no? That's equal to KQ over R. So, once again, this is the expression for finding the electric potential at a point due to a point charge. So, dito, ang ginawa nating reference point ay infinity. And at that point, the electric potential is 0. Okay, so tatandaan ha, kapag ka electric potential ang kinukompute, dapat meron pa rin tayong reference point. And for convenience, that reference point is set to infinity. Or in electric circuit analysis, that is the ground. No? So anong common dun sa infinity at saka sa ground? Dun sa mga points na yan, ang electric potential ay 0. Okay? Ngayon, i-analyze natin yung mangyayari dyan sa electric potential na yan kung ang point charge ay positive at saka negative. Kung positive yung point charge natin, what will happen to the electric potential habang lumalayo tayo doon sa source charge? Ayan. habang lumalayo tayo outward, palayo ng palayo, doon sa positive na source charge, yung electric potential ay lumiliit. Pero kapag papalapit tayo doon sa source charge, ang electric potential ay lumalaki. So, the reverse will happen if we have a negative source charge. Okay? For a negative source charge, as we move away or outward from the source charge, the electric potential increases. And habang lumalapit naman tayo doon sa source charge, ang potential ay lumiliit. Okay? So by default, yung ginawa natin para yun sa isang positive na source charge. So kapag nag-negative, di baliktarin mo lang yung mangyayari. Di ba? Now, mag-solve naman tayo ng mga problems involving electric potentials and electric potential calculation. Sample number 1. A proton moves a distance d equals 0.5 meters in a straight line between points A and B in a linear accelerator. The electric field is uniform along this line with a magnitude of 1.5 times 10 to the 7 volts per meter in the direction from A to B. Letter A, determine the force on the proton, and letter B, determine the work done on it by the electric field, and letter C, what is the potential difference VAB? Okay, so to solve this problem, let's start with letter A. Solve for the force. That force is equal to the magnitude of the charge multiplied by the electric field. Okay, so since we have a proton, we know that a proton has a charge equal to the magnitude of the electron's charge. Tapos imumultiply lang natin yan dito sa 1.5 times 10 to the 7. Pwede naman na-erecta na natin yan sa calculator. So Q is the magnitude of the electron's charge, which is constant 23 sa calculator. Multiply natin ng electric field na 1.5 times 10 to the 7. Okay, so we got 2.4 times 10 to the minus 12. 2.4 times 10 to the negative 12 newtons. Okay, maliit lang na force yan. Siyempre, maliit lang din yung magnitude ng charge. Now, for letter B, tinatanong naman tayo, ano daw yung work done on it by the field? Remember that the work done is equal to this force multiplied by the displacement, no? So, that's Q, E times D. Straight line naman yan eh. So, yung angle natin ay 0. So, yung QED cosine theta is cosine 0, which is 1. Kaya ang matitira na lang is QED. Okay? So, meron na tayong force. I-multiply lang natin yan ng displacement, no? Which is equal to 0.5. So, yung sagot natin sa CalQ, multiply lang natin ng 0.5. Ang sagot is, ayan, 1.2 times 10 to the negative 12. Diba? 1.2 times 10 to the negative 12. Siyempre, 0.5 is kalahati. Kalahati ng 2.4 is 1.2. Ang unit niyan, of course, is joule because it's work. Next, letter C. Ano daw ang potential difference? The potential difference, VAB, is the work done per unit charge. Diba? Ito na yung work. Kapag yung work na yan, dinivide natin ng charge, which is yung magnitude ng charge ng proton, makukuha natin ngayon yung potential difference. So, this is the work done. I-divide lang natin yan ng constant 23. Kasi yung constant 23, yun yung magnitude ng charge. So, ang makukuha natin is, ayan, 7.5 times 10 to the 6. 7.5 times 10 to the 6 volts. Or, pwede natin yung isulat in terms of an engineering prefix, 7.5 megavolts. So, sa isang linear accelerator, ganyan pala kalaki yung voltage. Yes, actually, it's a high voltage equipment para yung mga charged particle ay mag-acquire ng napakalaking value ng acceleration. Okay? So, madali lang. Next, example number 2. We have a 12-volt battery which is connected between two parallel plates separated by 3 centimeters. So parang ganito palang istorya niyan. Meron tayong dalawang parallel plates. Okay? Considering ito yung dalawang parallel plates, side view na lang. Tapos sa pagitan nila, meron daw tayong 12 volts battery. So imagine, may 12 volts sa pagitan nito. Lagyan natin halimbawa, ito yung voltage. Okay? 12 volts. Tapos syempre, ito yung positive at ito yung negative. Okay? Now, an electron is released from rest at the negative plate. So ito yung negative plate ngayon. Lagyan natin dyan ng electron. Halimbawa, Ito yung electron. Ayan. Ang electron na yan, ni-release from rest dito sa negative plate. Ano daw ang magnitude ng electric field between the plates? Dahil meron tayong voltage source dito, sa pagitan ng plates, magkakaroon tayo ng electric field. Ayan. Itong electric field na to, pwede nating i-assume na uniform. Okay? Uniform ang electric field. So, ang magnitude ng electric field na yan, paano natin malalaman? So remember that the electric field has a unit of volts per meter. No? Di ba meron tayong unit na newtons per coulomb, equal din yan sa volts per meter. So, yung electric field na yan ay equal dun sa potential difference between these plates. How many volts ba yun? Di ba 12 volts? Yes. So, 12 volts divided by, ano ba yung separation ng dalawang plates? 3 centimeters. So, 0.03 meters. So, yung 12, pag dinivide natin ng 0.03, ang makukuha natin dyan is 400. So, we have 400 volts per meter. Yan ngayon yung electric field dito sa pagitan ng dalawang parallel plates. Okay? Now, yung electric field na yan ay uniform. No? Uniform yan. Pero sa totoong buhay, dito sa gilid, yan ay nagka-curve. Gumaganto siya. Ayan. Nagka-curve yan. Doon sa gilid. Pero kapag ikaw ay wala sa gilid, no? You are at the middle or close to the middle, then pwede tayong mag-assume na constant yung electric field. Ganyan ang nangyayari sa isang parallel plate capacitor. Ano? Ang tawag dito is actually fringing effect, yung pag-curve ng electric field dun sa gilid ng parallel plates. So dito, hindi na natin masasabi na yung electric field ay uniform. Bakit? Kasi kita natin na curved na yung mga electric field lines. So para safe, inassume natin na yung electron ay nandito, no? Wala sa gilid. Nandito siya malapit sa gitna or sa gitna, dito siya ni-release from rest. Tapos siya ay gagalaw ngayon papunta dun sa positive plate. Lagyan natin dito ng arrow. Yan. Gagalaw siya papunta doon sa positive plate. Sa letter B, ano daw yung acceleration ng electron? Sir, bakit magkakaroon ng acceleration? Natural, may electric field. Due to the field, magkakaroon ng force. At dahil may force, mayroong acceleration. And that acceleration is equal to the force divided by the mass. Okay? This force is equal to QE. Kopyahin ko lang yung mass. Ayan. So, compute na natin ngayon, no? Sa calculator, Q is yung charge ng electron, no? So, we have constant 23 times electric field natin na 400, i-divide natin ng mass ng electron, constant 0.3 yan. And equals, so we have 7 times 10 to the 13. Okay? The acceleration is 7.0 times 10 to the 13 meters per square second. So we round our answer to 2 significant figures. Store natin yan sa calculator. Okay, mukhang gagamitin natin siya later. For letter C, ang hinahanap, ano daw yung velocity na kanyang na-acquire? So yung velocity niya, syempre, na-acquire niya pagdating niya dun sa kabilang side. No? Dating niya dun. Okay? So, paano natin yung malalaman? Meron tayong equation sa kinematics, di ba? Yung Vf squared is equal to Vi squared plus 2AD. So, initially, at rest yung electron natin because it was released from rest. So, we can determine the final velocity. That's equal to the square root of 2AD. So, erekta na natin yan sa calculator. Ano? Square root of 2 times yung acceleration niya na nakastore sa A times yung displacement niya na 3 cm, 0.03 meters equals, ayan, meron tayong value na 2.05. Bf is equal to 2.05 times 10 to the 6 meters per second. Okay, sobrang bilis ng final velocity ng electron. Ano? Biruin mo, more than 2 million meters per second. So kung siya ay magta-travel mula negative to the positive plate, dahil napakabilis niya at maliit lang naman yung distance, siguro yung makukuha nating time interval ay napakaliit din. Yes, no? Dapat maliit lang ang makuha nating time interval. So computein natin yan. Paano? Remember that in kinematics, we also have the formula that Vf is equal to Vi plus A times T. Right? So we know that this initial velocity is 0. We can solve for the time interval if we divide the velocity, which is this velocity, by the acceleration na nakuha na natin kanina. Ano? So yung answer na yan i-divide ko lang ng acceleration na na-compute natin kanina, yung time interval na makukuha ko is, ayan, 29.2 nanoseconds. 29.2 nanoseconds. As expected, napakaliit na time interval lang. Bakit? Kasi nga po, maliit lang yung distance na na-travel niya at ang kanyang velocity ay napakabilis. Pero halimbawa, hindi niya tinanong yung acceleration. Hindi niya tinanong yung electric field. Rekta ang itinanong niya, ano daw yung velocity niya. No? Ano ang kanyang final velocity nung narating niya yung positive plate. Meron ba tayong alternative solution para directly makuha natin agad yung final velocity without having to solve for the acceleration? Actually, yes, no? Dito gagamit na tayo ng energy analysis. Compute natin yung final velocity directly without having to solve for the acceleration and the electric field. Paano yan? We can use the work energy theorem, which states that the change in the kinetic energy is equal to the net work done. Okay? Now, the change in kinetic energy is equal to 1/2 times m, then Vf squared minus Vi squared. And the net work done can be obtained because we know that we have the potential difference. Remember that the potential difference, VAB, is equal to the work done per unit charge. So if I multiply the charge by the potential difference, that's the net work done. Okay? So we have Q multiplied by VAB. Now, ang gusto nating malaman is yung final velocity, 'di ba? Ito initially 0 yan eh, no? So, from this equation, mako-compute natin yung final velocity. Rekta na natin yan sa calculator. Okay? So, sa calculator, since ito ay naka-square, magkakaroon tayo ng square root. Tapos, fraction sign. Ano? Itong 2 dito, mapapapunta doon. So, that's 2 multiplied by Q, which is yung charge ng electron. Constant 23 uli, multiplied by the potential difference. Na magkano? 12 volts. Okay? I-divide natin siya ngayon ng mass. Yung mass ay constant 3 kasi mass ng electron, di ba? So, dapat ang makuha nating sagot, kagaya lang din ito, 2.05. Okay, ayan. So, the answer is just the same, 2.05 times 10 to the 6. But, using energy analysis, mas nakuha natin directly yung final answer without having to use kinematic equations. Di ba mas madali yon? Yes. Okay, so let's solve another problem. Example number 3. We have a point charge, 450 nanocoulombs, located at 2, negative 3, 5. What is the electric potential at point A? So, in this problem, wala tayong nabanggit na ibang other points. No? Yun lang location ng point charge at yung location ng point kung saan hinahanap ang electric potential. So, that means, kinakailangan nating mag-assume na ang reference point natin ay infinity kung saan ang electric potential ay 0. 'Di ba? So, in that case, pwede natin gamitin yung formula ng electric potential na V is equal to K Q over R. Okay? So, madali na lang ito, ano? Yung K natin is 9 times 10 to the 9. Since yung Q natin ay nano, yung to the 9 at to the negative 9, magka-cancel yon. Kaya ang isusulat ko na lang is 9 times 450 divided by yung R. Okay. Yung R naman, pwedeng irekta na natin yan sa calculator eh. Ano? So, compute na natin ha. Okay. 9 times 450. Yung R natin, square root of, okay, negative 4 minus 2. That's negative 6. Negative 6 squared is 36. Tapos plus 0 minus negative 3. That's positive 3. Positive 3 squared is 9. Tapos plus 2 minus 5 is negative 3. Negative 3 squared is 9. Ayan. So, ito na yung KQ over R natin. Equals, ayan. May nakuha na tayo right away. Ang sagot is 551.1 volts. Okay, 551.1 volts. Ayan, this is the electric potential at point A, assuming na yung reference point natin ay infinity, kung saan doon sa infinity, 0 ang ating electric potential. So, bakit tayo nag-assume na sa infinity 0 ang electric potential? Kasi wala namang ibang points na nabanggit sa problem, no? Na pwede nating gawing reference point. Kaya nag-assume tayo infinity yung reference point. Okay? Next problem, number 4. Find the electric potential at point P. So dito meron tayong dalawang source charges. Yung isa ay positive 2 microcoulombs at yung isa naman ay negative 6 microcoulombs. So dalawa. So kung dalawa yung source charges, paano nagko-compute ng electric potential? Eh di i-add mo lang sila. Now, the good thing is, electric potential is a scalar quantity. So, pag nag-add tayo, wala nang kailangang unit vectors. Addition lang ito talaga. Ano? So, kinakailangan i-consider natin yung sign ng charge kung siya ay positive at saka negative. Ano? So, the total potential at point P is equal to K times Q1 over R1 plus K times Q2 over R2. Pwede naman natin yung erekta sa calculator? Actually, yes. So sa calculator, pindutin ko na lang yung K kasi common factor naman siya. Ano? 9 times 10 to the 9 times parenthesis. Okay. So, dun sa una, Q1 over R1. Assuming ito yung Q1 ko. Ano? Positive 2 microcoulomb. So, ilalagay ko lang 2 times 10 to the negative 6 divided by, gaano siya kalayo sa point P? Ayan, 4. So, 4. KQ over R. Tapos, plus. Then, pangalawa, common factor yung K. Yung Q2 natin negative. Isasama natin yung sign. Negative 6 times 10 to the negative 6. Kasi micro. Divided by, gaano kalayo ito dun sa point P? Ito ay 4. Ito ay 3. Di ba special right triangle yan? 3, 4, 5. Okay, so the distance is 5. Ayan, parenthesis and then equals. Ay, may nakuha tayong electric potential na negative. Negative 6,300 volts. Negative 6,300 volts. Or, gawin nating negative 6.3 kilovolt. O di ba madali lang? Kung electric field yung kinompute sa point E, abay hindi ganun kadali kasi kinakailangan yung i-add mong electric field ay vector, no? So, ang kagandahan dito, yung electric potential ay scalar. Okay, so kung tatlo sila, ganun din ang gagawin mo, i-add mo yung pangatlo. Okay, kung apat, ganun din. Okay? Next, example number 5. An electric dipole consists of point charges Q1 equal to 12 nanocoulombs and Q2 equal to 12 nanocoulombs pero negative. 'Di ba? Ito yung dipole mo, no? Equal in magnitude but opposite polarity. One is positive and the other is negative. They are 10 centimeters apart. Ano daw ang electric potentials at points A, B, and C? Ayan. So, computein lang natin ha, yung electric potential at A. So, lagay natin dito. At point A, yung electric potential is, okay, i-add lang natin yan, di ba? At point A, the electric potential is the sum of the potentials due to Q1 and Q2. Rekta na natin yan sa calculator. 9 na lang yung ilalagay ko, tapos parenthesis, unang Q. Kasi nanocoulombs to eh. Yung to the 9 at to the negative 9 magka-cancel na siya. So 12 divided by, gaano kalayo yung Q1 mula sa point A? 6 cm. So 0.06. Tapos plus. For Q2, we have negative 12. Tapos gaano siya kalayo yung Q2 mula sa point A? 4 cm. 0.04 meters. Okay. Close parenthesis equal. So we have negative 900. No? Negative 900 volts. Next, at point B, B equals, so sa calculator, palitan lang natin ito, ano? Okay. So sa point B tayo naghahanap ng electric potential, no? Ang Q1 12 pa rin, ang mababago lang dito is yung distance, no? 4 cm siya. So gawin ko itong 0.04. Yan. Tapos plus due to Q2 which is still negative 12, mababago lang yung distance natin. Gaano kalayo yung point B doon sa Q2? So we have 10 plus 4 is 14. So this is 0.14 meters or 14 centimeters. Equals, ayan, ang sagot natin is 1928.6. Okay? 1928.6 volts. Next, at point C, ito yung point C. And we can see that point C is equidistant from these 2 point charges. So pag kinompute natin yung KQ over R squared, no? Due to Q1 at saka Q2, equal ang magnitude. Pero opposite ang polarity. Kaya magsisiro yan, ano? So, Ang potential nila, parehas ang magnitude. Pero since opposite ang polarity, magka-cancel. That's why at point C, the electric potential must be 0. Okay? Now, may pahabol dito eh. Ano daw ang potential energy associated with a 4 nanocoulomb charge placed at these points? Ibig sabihin, halimbawa at point A, meron ka daw 4 nanocoulomb na charge. Ano daw ang electric potential? Madali lang yan. Remember, how do we define electric potential? Electric potential is the potential energy per unit charge. So, kung gusto nating malaman ang potential energy, ito yun eh. No? U is equal to Q multiplied by V. Ayan. So at point A, yung U natin ay equal dun sa Q, which is 4 nanocoulombs multiplied by 900 volts. Ayan. So, lagay lang natin dito, negative 900, yung kanina, na volt na potential, multiply natin ngayon ng charge na 4 nanocoulombs, negative 9. Ayan. Meron tayo ngayong negative 3.6. Okay, negative 3.6 times 10 to the negative 6 joules. Next, at point B, ito yung potential natin, 1928.6. 1928.6. Multiply pa rin natin ng 4 nanocoulomb. So, 4 times 10 to the negative 9 equals, we have 7.7. So, U is equal to 7.7 times 10 to the negative 6 joules. Next, at point C, since the potential is 0, the potential energy must also be 0. O, diba? So, nakapag-solve na tayo ng electric potential at a point, nakapag-solve na rin tayo ng potential energy at that point. Okay? O, diba? Madali lang. Next, example number 6. A point charge of 5 nanocoulombs is located at the origin. If V is equal to 2 volts at 0, 6, negative 8. Ano daw ang potential at point A? Ano daw yung potential at point B? At ano daw ang potential difference na VAB? Okay. So, dito, meron tayong isang point kung saan given ang potential. Ano? Given yung point na 0, 6, negative 8 at dun daw sa point na yan, ang potential ay 2 volts. So, lagyan natin ng representation ito ha. We let that point 0, 6, negative 8 be equal to, for example, point X. Okay? And at point X, the electric potential is 2 volts. Okay. Tapos meron daw tayong point charge sa origin, 5 nanocoulombs. Ano daw ang potential at A? Ano ang potential at A? So kung meron tayong isang point kung saan given ang potential, yun ang gagawin nating reference, 'di ba? And remember, kanina yung reference, yun yung pangalawang subscript. Okay? So, pwede nating isulat dito. Meron tayong VAX. Okay? Ito yung A. Tapos, meron tayong point X. At yung VAX na yan, we know that it's equal to VA minus VX. Right? So, from this, magkakaroon na tayo ng expression para makompute yung potential at point A. The potential at point A is equal to VAX plus VX. Pero ano yung VAX, 'di ba? Meron tayong unknown dito na VAX. Para malaman yung VAX na yan, we need to consider that we have a point charge which is located at the origin. Kung point charge, ano ba ang expression ng potential difference? 'Di ba kanina meron tayong VAB due to a point charge which is equal to KQ times 1 over RA minus 1 over RB? Yes. So, gagamitin natin ito. Okay? Para sa VAX. Sige, gawin natin yan. VAX is equal to KQ multiplied by 1 over R at point A minus R at point X. Kasi AX eh, no? Kanina AB kaya RA tsaka RB. Ngayon naman AX kaya RA at tsaka RX. Okay? Kaya na ba natin gawin yan sa calculator? Yes, pwede na natin yung erekta sa calculator. Since yung ating point charge ay naka-nanocoulombs, ganito na lang. 9 na lang yan, ano? KQ, 9 times 5. Multiply natin ng 1 over, ano yung RA? RA is the distance of point A from the source charge, which is located at the origin. Okay? So that must be equal to the square root of Ang origin kasi 0, 0 ang coordinate niyan, ano? So, ito na lang minus yung coordinate ng origin na 0, 0, 0. So, magiging -3 minus 0, -3 squared is 9. Tapos plus 2 squared is 4. Plus 6 squared is 36. Ayan. Tapos, minus 1 over, what is Rx? Rx is the distance of point X from the origin. Where is point X? This is our point X, right? So that's the square root of 0 minus 0, 0. Yun na lang, 6 minus 0, yung origin, 36. Plus negative 8 squared is 64. Close parenthesis equals, ang sagot, we have 1.93. Ayan. VAX is 1.93 volts. Dahil meron na tayong VAX, makukompute na natin ngayon yung VA. Diba? Remember that VA is VAX. So we have 1.93 volts plus yung VX natin na 2 volts. So the answer is 3.93 volts. Okay. O ayan, meron na tayo ngayong VA. Tapos dito may pinapahanap siya. Ano daw ang potential at point B? So actually, ganun din yung gagawin nating proseso. Kuhanin muna natin yung VBX, which is equal to VB minus VX. Tapos from that, yung expression para sa VB is equal to VBX plus VX. Okay? Tapos sa calculator, makukompute natin yung VBX. Yung VBX, sulat muna natin yung expression, that's KQ times 1 over RB minus 1 over RX. Okay, sa calculator, gawin natin yan. Ano? Ito yung K, ito yung Q. Tapos, palitan lang natin yung distance. Yung RB kasi, distance yan ng point B mula sa origin. Okay? Nasaan ba yung point B? Point B is at 157. So, 1 squared is 1 plus 5 squared is 25 plus 7 squared is 49. Tapos, palitan natin yung denominator ng pangalawang term. No? Ano ang distance ng X or point X mula sa origin? Actually, yun pa rin yun, no? So, pa rin yung 36 at saka 64. Dito siya galing. So, mag-equals na lang tayo dito. Equals, ayan, ang sagot, 0.696. Okay, so VBX is 0.696 volts. So, if we know VBX, makukompute na natin yung VB. No? So, VB is equal to this VBX plus VX. Eh, di ba alam natin 2 volts yan, no? Pag dinagdagan natin to ng 2, magiging ano lang siya, 2.696, di ba? 2.696 volts. Okay, so we now have the potentials at point A and the potential at point B. And yung huling tanong, ano daw ang potential difference na VAB? Madali lang din yan. Yung VAB, equal lang siya sa VA minus VB. Diba? So, meron na tayong na-compute na VA, meron na tayong na-compute na VB. So, 3.93 minus 2.696. Ang sagot is, ayan, 1.234. Okay? So, this is 1.234 volts. That's it. Ganun lang po kadali. Diba? So, dito, hindi tayo pwedeng mag-assume na ang reference point ay infinity, kung saan 0 ang electric potential doon. Bakit? Kasi po, may given point, ayan no, may given point kung saan nabanggit niyan ang electric potential daw ay 2 volts. Kaya yung point na yon ang gagawin nating reference. No? Na dito sa problem na ito, ginawa nating point X at yung point X ang ating reference. Remember, in the notation for the potential difference, ang reference is yung second subscript. Okay, kaya meron tayong VAX at meron tayong VBX dito. Okay? So, madali lang yan. Practice ka lang. Example number 7. Last example na ito. Find the potential difference between 2 points A and B having radial distances RA and RB from a very long line charge with a uniform charge density lambda. Assume that RA is greater than RB. Okay, so dito, meron tayong line charge, very long. So, kung yan ay very long, pwede nating i-assume infinitely long siya. Ano? So, hindi na ngayon point charge yung source ng potential natin. Kanina kasi, yung mga kinukompute nating electric potentials is due to a point charge, but this time, meron tayong line charge. na may uniform charge density na lambda. Tapos meron daw tayong points A at saka B. Halimbawa, ito yung dalawang points, A at saka B. A at saka B. Pero ang sabi niya, RA is greater than RB. Ito yon halimbawa. Okay? This is your RA. Yan. At ito naman yung RB. Because RA is greater than RB. So this is your point A and this is your point B. Ayan. Ano daw ang potential difference? VAB. O, di ba? Yun ang hinahanap dito eh. So we have the potential difference VAB due to an infinitely long line charge. So pwede tayo ditong mag-assume yung line charge na yan positive ang charge density. So remember that this VAB is equal to the negative of the integral of E dot EL. This is from B to A. Okay? Now, what is the expression for finding the electric field due to a very long or an infinitely long line charge? Di ba pinag-aralan natin yan sa electric field calculations? That E is equal to 18 times 10 raised to 9 multiplied by lambda over x. But this time, yung distance natin is r. Kaya ang gagamitin ko is r, lambda over r. Okay? Tapos yung differential natin is, yung dl is dr. Okay? Kinancel ko na yung mga unit vectors na ar at saka AR because AR is just 1. Okay? I-indicate natin ngayon yung limits natin from B to A. So at point B, your distance is RB. And at point A, that's RA. Okay. So ito lang siya, I-integrate lang natin ito. Madali lang naman, Kasi ito naman ay constant, 'di ba? Pwede nating ilabas na agad 'yan. VAB is equal to negative 18 times 10 to the 9 times lambda. Now, kapag integrate natin yung dr over r, di ba ln yan? So, dito magkakaroon tayo ng ln of, times ln of upper limit, ra, minus ln of rb. Di ba? Remember, may property yung ln natin. Itong ln of ra minus ln of rb, pwede nating isulat as ln of ra over rb. Okay? Sulat natin yan dito ha. VAB is equal to negative 18 times 10 to the 9 lambda times ln of RA over RB. Okay? However, since meron tayong negative dito, para hindi natin makalimutan yan, kasi makalimutan mo pa yan sa pagsusulat mo, tanggalin na lang natin. Now, to remove this, pagpalitin lang natin itong numerator at denominator. If we interchange these two, the effect is multiplying this by negative 1. So, negative times negative, magiging positive. Mawawala na yung negative sign. Diba? So, VAB is equal to 18 times 10 raised to 9 lambda ln of RB over RA. That's it. We now have the expression for finding the electric potential difference between 2 points due to a very long line charge na mayroong uniform charge density. Okay? So baka itong expression na to ay ma-encounter mo kapag inaral mo yung coaxial cable. Pag halimbawa kinompute mo yung voltage sa pagitan ng inner at saka ng outer conductor, itong expression na ito ang gagamitin mo. Again, sa pagko-compute ng voltage sa pagitan ng inner at outer conductor ng isang coaxial cable. Okay, so as I have said, this is the last example for this lecture and I hope that you enjoy the topic, At sana ay mag-practice kayo na mag-solve ng mga similar problems so that when the examination comes, you are well prepared and you can answer the questions correctly. Until the next video, thank you for watching. Bye!